All right, so today we're going to talk about glycogen synthesis. And if we remember our three steps from glycogen breakdown, we had mobilization, debranching, and mutation. And we talked about the three enzymes responsible for those. We talked about phosphorylase, we talked about the debranching enzyme, and then we talked about phosphoglucomutase. So we're going to kind of think about this same picture of glycogen, and we'll think about three steps in terms of reversing the process for synthesis. So those three steps are going to be activation, polymerization, and branching. So ultimately, if we're going to hook things together, we have to have some way of activating them so that we can create that bond. So again, activating our monomers, polymerizing them so that we can make polymers from these monomers. And then again, how do we add in those branches? So we'll talk about several aspects of that in today's activity. So if we look at the opposing pathways of glycogen breakdown and glycogen synthesis in terms of what we refer to as a substrate cycle, hopefully we can kind of think about these two as opposing pathways that obviously aren't going to operate at the same time. So again, as we learned about with the breakdown of glycogen, and these enzymes aren't necessarily in the order that they occur in. Again, it's not necessarily that it's a linear progression, but remember that glycogen phosphorylase is going to chew in from the ends until it reaches a branch point. Then we need to have that debranching enzyme both move part of that limit branch as well as eliminate that alpha-1,6 linkage, and so it eliminates that glucose residue that's right next to the branch point. And then once we have about 10% as free glucose and the rest of that 90% as glucose 1-phosphate, phosphoglucomutase is going to then convert it into G6P, our branch point metabolite. So that's again breakdown. Thinking about synthesis in the reverse kind of process, we have to think about what our starting molecule would be, and since G6P is an important branch point metabolite, if we've got excess glucose in your bloodstream, you're going to pull it into your cells, you'll have to phosphorylate it to make it into G6P, and then now that G6P as a substrate is ready to be polymerized into glycogen. But we first need to make it into G1P. We need to activate G1P in order to get it to be ready to polymerize, and then we need to polymerize GDP, glucose 1-phosphate that's been activated as UDP-Glucose, so we need to polymerize that, and then we need to add in our branches. So in some ways there's kind of 4 steps because we first have to convert any available G6P into a non-glycolytic intermediate G1P. So again, we've got phosphoglucomutase, but we didn't have that kind of as part of our 3 steps here. So we're assuming we already have G1P. We're going to activate it into a monomer that's going to be able to be condensed, so UDP-glucose. Glycogen synthase is again the enzyme that we're going to learn about that's responsible for doing this polymerization, creating those alpha-1,4 glycosidic linkages. But again, once we create that linear polymer, then we're going to have to add in branches, and we do that by a branching enzyme that kind of does the reverse of what we saw with our debranching enzyme. It's going to take the end of a polymer and move it and create an alpha-1,6 linkage. So we'll talk about all these processes, but big picture here, one of the things we have to remember is if we have 2 things going in opposing pathways, if one of them is kind of downhill thermodynamically to go in one direction, as we saw with the breakdown of glycogen, that's a thermodynamically favorable process, goes downhill in energy. We can't go in the opposite direction and also have that be downhill. Right? That's energetically impossible. So what we do is we choose an alternative pathway, so we have different enzymes then, and then we have to input energy. And that energy comes in the form of UTP that's able to activate this glucose residue as UDP-glucose, so it's going to be able to be polymerized. So we'll go through this in some detail. We'll practice this in our activity. The first thing that we'll do is we'll look at not the breakage of a glycosidic bond, but the formation of a glycosidic bond. So we're going to reverse that mechanism we did in our glycogen breakdown activity. And we're going to talk about the acid-catalyzed condensation of a hemiacetal, again, with an alcohol to yield that acetal. So again, looking at this in a very generic sense, we'll draw out this mechanism, but a theme that we'll kind of see here is the reason that this chemistry happens is we protonate water, or we protonate our alcohol here, get a good leaving group, create a very electrophilic intermediate that's susceptible to creation of that new carbon-oxygen bond. So the concept is, well, all we have to have is a great leaving group. And so the theme that we'll see with carbohydrate condensation reactions is that we're going to use NDP sugars. So we're going to use sugars that have a nucleotide diphosphate that's added onto that oxygen here. So it'll be an O-NDP. And again, that NDP is just a good leaving group, so it allows us to participate in this chemistry. So again, UDP-Glucose Pyrophosphorylas is our enzyme that's responsible for this activation. So we're in a three-step process: activation, polymerization, and then branching. So this is step one. UDP-Glucose Pyrophosphorylase, that's a mouthful, but ultimately what we have is we have UTP here as our energy source. We've got glucose 1-phosphate that we have here. So remember, we had to take glucose 6-phosphate and first mutate it to make glucose 1-phosphate. We've got this phosphate here that we're going to add this Actually, we're going to be adding UMP, but since there's already a phosphate there, it's going to generate UDP glucose. And again, I've highlighted here that UDP is going to be a very good leaving group. But what's really neat about this reaction is when we add and do some chemistry on this alpha phosphorus of UTP, this pyrophosphate group, again, is a decent leaving group. And then there's lots of inorganic pyrophosphatase. That's an important enzyme that just kind of is ubiquitous in your body. Anytime you have this type of an activation reaction, this pyrophosphatase is going to rapidly hydrolyze this pyrophosphate to make 2 inorganic phosphates, and that imparts a level of irreversibility to your reactions. And that's important because it drives this thermodynamically forward to allow us to create a significant amount of this activated monomer that we can then couple together. So as I highlighted on our previous slide, the theme is that we're going to see these activated monomers being used to synthesize polymers, not just in carbohydrate chemistry. All right, so we've done our activation. Now we need to do our polymerization. That happens with an enzyme called glycogen synthase. So we'll talk about regulating glycogen metabolism with both phosphorylase and synthase. These are the 2 rate controlling steps for the forward and reverse processes here. So synthase is the rate controlling step for glycogen synthesis. So basically how it works is it takes this molecule that has a really good leaving group. The leaving group is going to leave, again, via assistance of this internal set of lone pairs on this oxygen atom, generates a very electrophilic oxonium ion intermediate, susceptible to nucleophilic attack by a growing glycogen polymer. That C4OH group is going to nucleophilically attack this very electrophilic oxonium ion intermediate and generate our alpha-1,4 glycosidic bond. We've extended our glycogen particle by 1 residue. Again, we talked about glycogen particles having about 120,000 residues. So this type of a coupling chemistry is going to happen very readily. We'll talk a little bit more about this in class than I'm going to present here, but the idea is we've got this synthase enzyme that can only add to something that you have 8 residues already there. So the question is well, how do you add to a glycogen residue with synthase if you don't have a glycogen residue to start with? Well, it's solved by having this glycogenin particle here. This is a small protein that actually has a little piece of like 8 residues of glucose hooked together with alpha-1,4 glycosidic linkages to look like a little mini piece of glycogen. And then you build your glycogen particle off of that. So remember when we talked about there being only one reducing end on our giant glycogen particle? Well, really that one end is attached to this protein called glycogenin. We're not going to talk a lot about regulation of synthase. As we'll see, it's much more important to talk about regulation of phosphorylase. But synthase is subject to both covalent modification and structural allosterism. So just like you might imagine, if phosphorylation will activate phosphorylase, phosphorylation will actually inhibit synthase. So again, we wouldn't expect that phosphorylation would activate both the breakdown and synthesis of glycogen. So phosphorylation of glycogen makes synthase B. That little italicized B tells us that it's the less active form. So we're going to see this figure again. We'll talk about it more in our activity in terms of how do you create these branches. And again, branching is going to be the next important point to think about. We had a debranching enzyme that allowed us to break apart branches. When we're making glycogen, we have to have a branching enzyme that's going to allow us to create those. So again, our glycogen branching enzyme is going to take these branches that are fairly long from synthase activity, and it's going to transfer them to the C6 OH group that we're going to have on some branch point here. And there's some rules, again, that we have to have here. We have to have at least 5 residues or 4 residues between where we have an existing branch and we're going to make a new one. And then when we remove kind of a branch here to transfer it, we have to leave at least 5 residues. Here we've left 6. So some rules to think about. We'll talk about this a little bit more when we have our activity. So this again is a slide I'm not going to spend a lot of time on here. We'll get to this in our activity. But the idea is when you are optimizing branching patterns, you need to think about 2 things: how close your branches are together and how long your individual branches are. And those 2 pieces are going to allow you to maximize storage space and mobilization speed. So storage space is you want to put in, again, the maximum number of glucose residues in your glycogen. If you put too much branching in, you're going to crowd out your particle quickly and you can't get it to be very large, so that limits your amount of glucose. However, if you don't branch enough, that's going to minimize the number of non-reducing ends you have. And again, you can't rapidly mobilize if you don't have non-reducing ends. So again, in our activity, we'll tease that out a little bit more. So this next section on control of glycogen metabolism, if you feel like you're really good on understanding pKa, if you feel like you're really good on understanding phosphorylase regulation, you can skip over this part, but I'm going to try to review things that we've learned before in chapters 12 and 13 on glycogen metabolism. So again, thinking about time of plenty or time of need, those are terms that we'll use a lot. If we're talking about glycogen metabolism in times of plenty, you've got high blood sugar levels. We're going to upregulate enzymes that are going to allow us to synthesize glycogen until we've reached kind of the maximum storage capacity. And again, if we've got low blood sugar levels, times of need, now those enzymes that will be upregulated are the ones that are going to allow us to break down glycogen, specifically glycogen phosphorylase. Purpose, again, to generate energy. As we just talked about with glycogen synthase, and we learned last time with glycogen phosphorylase, and we'll review here, both are subject to allosteric control, right? Small molecules binding to and regulating R state, T state of our molecule, and covalent control, adding and removing phosphates, regulating the activity of our enzymes. And as we see here, we're differentially regulated with phosphorylase and synthase. If we phosphorylated these, phosphorylase will be active, synthase will be inactive. All right, so I'm going to go through this very quickly. We got an activity from our glycogen breakdown class where the last page of that allows you to think about all our methods for regulating phosphorylase and pKa. So we're going to just kind of review those now. Pieces that we've already learned about, right? We learned about a signal cascade in chapter 13. We talked about protein kinase A, so remember that phrase, pKa phosphorylates phosphorylase kinase, phosphorylase kinase, phosphorylase phosphorylase, and phosphorylase breaks down glycogen, right? So we learned a lot about pKa, we learned a lot about glycogen phosphorylase. 2 players that we're going to learn about in this chapter to put the whole picture together are more details about how phosphorylase kinase works, and then importantly, a protein called phosphoprotein phosphatase 1, or PP1. That's the enzyme that turns this whole thing off. Now, we're not going to learn about that until our next lecture. So today, for the rest, we're going to just do a quick review of pKa, of phosphorylase, and then introduce some aspects of phosphorylase kinase. So, should look at this structure. You could say, hey, I know that's phosphorylase. Remember things with phosphorylase being more subjective to or more able to bind our substrate if we're in R state. Whether you're in R state or T state has to do with the position of this N terminus. And if this N terminus again is out, we're going to be R state. If we phosphorylated that serine 14 on that N terminus, that allows us to be R state, because not only do we not want to bury a negative charge, right? We want to make sure that that interacts with these some arginine residues that are here. So lots of ways that we stabilize the R state for phosphorylase, right? So again, details that we talked about before. Glycogen phosphorylase also subject to covalent modification, and these 2 again are superimposed. So this summary slide, I'm not going to read through all of it. Again, this is a review. If we are phosphorylated and that serine 14 has that phosphate on, we're going to be R state because we can't bury that N terminus. So again, being phosphorylated is going to allow us to also be in the R state. If we do not have that phosphate on, we can bury the N terminus, we can be in the T state. And remember, we talked about the concepts that even though this is a binary system that allows for 4 possible options, we really only funnel to 2 possible options: a dephosphorylated T state, which is the most inactive, or a phosphorylated R state, which is the most active. So if we've got a high blood sugar levels, resting state, or even elevated levels of ATP, that is going to allow us to exist in this dephosphorylated T state, and that makes sense. If you've got plenty of glucose around, don't be breaking down your glycogen. Need state, our blood sugar levels fall, right? Top-down approach, a way to remedy low blood sugar levels is to break down your glycogen. So again, we're going to allow ourselves to phosphorylate phosphorylase. That will allow it to persist in the R state and facilitate the breakdown of glycogen. And in our last lecture, we looked at the enzyme active site finally for glycogen phosphorylase and understood how that phosphorylase chemistry works, that phosphorylysis of that glycosidic bond. All right, again, another review slide, so I'm going to go really quickly here. pKa, also sometimes called CAPK. This, again, is the beginning part of our phosphorylation cascades. A need state signal on the external environment is going to allow for activation of our adenylate cyclase. That's going to increase concentrations of cyclic AMP, high levels of cyclic AMP, right? If we've got lots of cyclic AMP, that binds to the regulatory subunits of pKa and kind of allows them to dissociate from the catalytic subunits. We've got 2 free catalytic subunits now available to do chemistry. So we're going to look very briefly at the structures of the catalytic and regulatory domains. Right, remember this, the catalytic subunit of pKa. So again, this orange here represents a substrate that would be bound for phosphorylation. The pink and white domains here represent the substrate recognition domain. We're going to have some cationic residues like arginine, and then a small residue. And then we'll have some serine or threonine that's going to be phosphorylated, and then some bulky aromatic residue. That's kind of the coding sequence that says, hey, this substrate is supposed to be phosphorylated by pKa. So some other important things to point out here. We're going to have a threonine residue, right, that's phosphorylated. That's what we have right here. That allows us to properly orient the substrate. And then the phosphate for that phosphorylation actually comes from ATP. We can see ATP bound here in the enzyme active site. Here's the gamma phosphate that again is going to be transferred to our substrate to allow it to be phosphorylated. Again, really quick there, but hopefully that's a review. Regulatory subunit. So this magenta domain here for our regulatory subunit, that will bind to the same place that this orange is binding here. So when we have our regulatory subunit binding in the active site of pKa, it pretty much acts like a competitive inhibitor for it. So the only way that it can do that is if it's not bound to these cyclic AMP motifs. So again, if we have high levels of cyclic AMP, conformational change of our regulatory subunits allow it to pull that magenta piece out of the substrate binding site from the catalytic domain. And now the catalytic domain can go and phosphorylate whatever substrate it wants to. So again, very quick review there of stuff that we've learned about before with pKa. So now we're going to get into stuff that we haven't yet learned about, and that's phosphorylase kinase. So here's phosphorylase kinase. All right, phosphorylase kinase has 4 subunits. Okay, pKa had 4 subunits, but they were 2 catalytic and 2 regulatory subunits. Phosphorylase kinase has 4 separate subunits. So this is how we're going to represent it. Alpha, beta, gamma, delta. Okay. Alpha and beta are regulatory subunits, so they behave kind of like we saw in pKa with those R domains. We call them alpha and beta. We've got a catalytic domain here in this gamma domain. So there's 1 catalytic domain in this tetrameric protein. And then we have this delta domain. We've actually learned about delta already because we learned about Calmodulin in our chapter 13. So that Calmodulin allows us to be a calcium-dependent kinase. So what we're going to have here is we're going to have this tetramer that exists in an inactive form when all of these pieces are together. Okay? What happens when we both bind calcium and then phosphorylate our alpha and our beta subdomains here, our regulatory subunits. Now that allows for a conformational shift. Note how this is different from pKa. When we had our binding of cyclic AMP there, our regulatory subunits actually broke away and apart from our catalytic subunit. What happens here with these 4 subunits, they all stay together, but when we phosphorylate alpha and beta, and then the delta subunit binds calcium, we have a conformational change that now frees up the enzyme active site in our gamma domain. So again, we'll build on that more in our activity, but that's kind of introducing what happens here. What's really interesting about the gamma subunit is it's got a lot of structural similarity to what we saw for the catalytic subunit of pKa. Okay, but one of the things that I want you to note that's very different is if we look right here, remember that there was a threonine 197 that was phosphorylated in the catalytic subunit of pKa. What we have here is a glutamic acid residue replacing that threonine. So what's really neat here is now we have a carboxyl group in place of a hydroxyl, or when it's phosphorylated, a phosphate group. So what happens is that carboxyl group mimics a threonine that's been phosphorylated. What that does, it allows this catalytic subunit to always be on. Okay, so how do we have it be off then? Well, again, conformational change allows the removal of an autoinhibitor segment. So the catalytic subunit of phosphorylase kinase, when it's in a certain shape, it actually has autoinhibition. Remember we talked about competitive inhibition with the regulatory subunit of pKa? Well, what happens here is it actually will have its own kind of competitive inhibition with a portion of itself. But now when the alpha and the beta subunits get phosphorylated, when the gamma subunit binds calcium, conformational shift now allows that autoinhibitor domain to be removed, and now it's ready to phosphorylate its substrate. It's kind of neat to think about the coupling of calcium with this. Calcium is really important for muscle contraction, so we've kind of tied these two processes together. Your muscles are working a lot. You want to break down the glycogen that's in your muscles to provide the energy for that process. Again, just a little review of Calmodulin. We saw this in chapter 13. This is a very small protein that has 2 globular domains that are responsible for binding calcium. When they bind calcium, we see a significant conformational change. So again, those 4 subunits that we see with phosphorylase kinase, when we phosphorylate the alpha and the beta and we bind calcium to the delta, that's when we see this conformational change that allows for the gamma subunit to be active. So again, summary here for phosphorylase kinase. When we are in a fed state, calcium levels are low, pKa is quiet, so nothing's getting phosphorylated. Without that happening, we have that autoinhibitor domain binding within the gamma subunit. No kinase activity, so it's not phosphorylating phosphorylase, so no glycogen breakdown. Need state, right? pKa is phosphorylating the alpha and the beta subunits. That gamma subunit is binding calcium, whose levels have been elevated. And now we're going to have conformational changes. Notice all 4 of these pieces are still together, but we're binding calcium and we're phosphorylated on our regulatory subunits. So now that gamma subunit is active. And remember, that gamma subunit is going to be active no matter what, because it's got a glutamic acid in place of that threonine. All right, so that was a lot of information thrown at you. What we're going to do then in our activity is kind of really put all this together. You know how we say that protein kinase A phosphorylates phosphorylase kinase, phosphorylase, and phosphorylase breaks down glycogen. But now we understand the final player in this puzzle. We understand how phosphorylase kinase truly becomes active, and now we understand how calcium comes into play. And that's it for our phosphorylation cascade with regulating glycogen metabolism.